Hi, we are going to do today the transistors, as tomorrow is your exam. So I'll first wish you all the best. Let's begin with the transistor. It's going to be very important. Discussion always comes up with of 5 marks or sometimes of 3 marks, but it's one of the short question for CBSE examination. Let's begin with the introduction of the transistor. It's a 3-terminal semiconducting device which is obtained by growing either a narrow strip of p-type in an n-type crystal or n-type in a p-type crystal. Are you getting me? I just wanted to say that it will be a narrow strip growing of a p-type in an n-type crystal. First we'll take an n-type semiconducting device and then we'll grow a small base of p-type. It's an NPN transistor having 3 terminals. That is why it is known as a triodes also. Right? They are also being known as the junction transistors or junction triodes. It's the emitter, base or collector. The symbol for the NPN transistor is one thing we need to remember, that the sign of the arrowhead is always towards the N side. Okay, so this is emitter, base and the collector. That's my NPN transistor. The other one, that is my PNP transistor. In the case of PNP transistor, once again we have a p-type semiconducting crystal and we grow a base of n-type in the middle of it. It's emitter, base and my collector. The symbol would be again of the similar kind. Once again the sign of the arrowhead would be towards the N side. Now as you can see, at this time my base is of N, so the sign of the arrowhead would be towards the base. That is my emitter and collector. Okay, now let's talk about the construction. Let's do it quickly with the construction. As I have the 3 devices, that is my emitter, base and collector. The very first one, that is my emitter. Emitter is moderate in size and heavily doped. Okay, so that it will provide large number of charge carriers to me, so that will give me a large number of charge carriers. Let's get to the base. It's the thin rigid which is lightly doped. Okay, now we'll talk about the collector. This is, in the case of collector, it is moderately dropped but it is large size. It's large size, moderately doped. Okay, so that is my emitter, base and collector. Now let's do the action of the NPN transistor. The probability of this coming up in the examination is not much, but if you are not aware about what is an NPN transistor and its action, how would you move towards the characteristics? Because maximum number of time that comes up in the examination is my action, that is characteristics, input and the output characteristics. Before I move towards that, first we'll discuss the action of the NPN transistor. Let's make an NPN transistor. We all know the configurations. We know the configuration. There are 3 types of configuration for my transistor. That is common base, which is also known as CB configuration, common emitter, which is also known as CE configuration, and the next one is common collector. That is my CC configuration. For the action, we will discuss only the CB configuration, while in our CBSE syllabus there is common emitter for the characteristics. So first we'll go ahead with the action of the common base transistor and then we'll move forward with the characteristics. So talking about the action, let's now do the common base NPN transistor. Let's make an NPN transistor. In NPN transistor, what do I have? I have an N-type crystal growing up a base of P in the middle of it. This is my emitter, this is my base, this is my collector. Okay, in the NPN transistor, we all know the majority charge carriers are electrons. In the case of base, the majority charge carriers are holes. And in the case of collector, again, there will be electrons. Now, to make this common base configuration, we will make base as common, which would be the part of the emitter battery as well as of the collector battery. So let's now make one of the junction being forward biased. This emitter base junction is need to be forward biased. For forward biasing, what do? We'll connect the N to the negative of my battery, and this base, which is P, is to be connected to the positive of the battery, so that this junction, this region will become the forward biased. Okay. Let's now make the another junction as reverse bias. To make this reverse bias, this needs to be connected to the negative of the battery for the reverse bias, and the another one need to be connected to the positive of the battery. Let's name these two batteries. Let this battery would be VEB or VBE, and let this battery would be VCB or VBC. Okay. Now, as soon as you will connect the battery, this junction, this emitter base junction is forward biased. Okay, this emitter base junction is forward biased, and my collector base junction is reverse. Now, if this is forward biased, as soon as I start increasing my VEB, as VEB increases, we will cross the potential barrier over here. Okay, for the forward junction, what do? We increases the battery. As soon as we crosses the barrier potential, the charges will start flowing from E to B. Charges will start flowing from N to P. Electrons will start moving towards the base. Okay, as this junction is forward biased, electrons will start flowing from the emitter to the base. Let's consider that 100 charge carrier start flowing from E to B. Okay, now as my base is very thin, okay, this is very thin, so what happened? Only out of 100, 5 charge carrier will combine with holes in B, and remaining will move towards the collector. As soon as a charge carrier will combine with the base, a electron hole pair would be generated by VEB, and this will give electron to my N region. Now, as the direction of electron would be this, the direction of my current would be opposite to this. We all know the direction of the current is always opposite to the flow of the negative charge carrier and of the flow of the positive, and holes will start drifting towards the base. So this is my current, and this constitute a current IE, and this constitute a current IB. Now, as soon as one electron will cross this junction and reaches to collector, once again an electron hole pair would be generated. A hole would be given by this battery to the collector, so that there will be neutrality of the charge carrier. The net configuration of the charges will remain the same, and an electron would be provided over here. So this IE will become equal to IB plus IC. This is one of my basic equation for the transistor, which is very important, and we need to remember this. At times numericals used to come up with this. Now, as this IB is very small, I can make IE to be roughly or approximately equal to IC. Okay. So this is the action of the NPN transistor. On the similar basis, one can also do the action of the PNP transistor. On the similar basis, one can do the PNP transistor. Let's now move forward with the characteristics, which is very, very important, and it used to come up. Before I'll move towards the characteristics of the common emitter transistor, first I would like to tell you the amplification factors or current gains. Okay, current gain, that is alpha. Sometimes numericals also comes up on this. Current gain alpha. So what is my current gain alpha? Current gain alpha is the change in output current. And what is my output current? That is delta IC. To change in my base current, that is my IB, when VCB is kept constant. This current gain is in the CB configuration. Okay. Now current gain beta, this current gain beta is in the CE configuration. Okay, what is that? In CE configuration, beta is given by change in output current, which is my delta IC once again, because collector is always giving me the output. In the case of base and common emitter, the common collector, it would be a little different. Beta is delta IC, that is change in the output current to change in the input current. Here my input current is delta IB. So delta IC by delta IB when my VCE is kept constant. Okay, this is alpha and beta. The relation between the alpha and beta is alpha is equals to beta upon 1 plus beta. You can just remember this result for the numericals. And let's now get to the common emitter NPN transistor characteristics. Let's draw it on the another sheet because we are going to require it for the characteristic. We'll study it. Okay. So we'll have a common emitter NPN transistor. Okay. Let's draw the diagram. This diagram is important. If this question comes up of the 5 marks, the 1 mark or more than 1 is off for this transistor diagram. So you'll draw it. Let's consider the NPN transistor. Now once again, if I have the NPN transistor, the arrow would be towards the N side. Okay, this is my emitter and this arrow is always on the emitter one, not on the collector. Okay, on the emitter line. This is emitter, collector and the base. Okay, this is NP. Let's mark it NPN with some another pen so that it will be easily recognized by you. NP and N. Okay. Now this base would be connected with the micro emitter as the current is very, very low. So we connected it with the micro emitter and we'll measure the voltage with a voltmeter over here. V1. We will connect it with a rheostat so that one can vary the value of current. Okay, we'll connect it with a battery. Let's now connect a milliammeter here. This milliammeter will measure the current IC. And then again a voltage V2 which will measure my output voltage. Okay. Once again this is connected to a rheostat which is connected to my original battery. Let's mark each battery and let's mark the flow of current. Okay. This is my base current which is coming from this side. Okay. So this is my IB. This is my IC. And this one is my IE. Right. This is V1 positive and negative which will measure my VBE which is my base emitter voltage. This is my V2 positive negative. This will measure my VCE. So this is VCE. Okay, once again I have a battery over here which is named as VCC and this battery is VBB. Okay, are you able to see clearly? Okay, it's not that much visible. Let's change the direction. Okay. Right. Let's now talk about the characteristics. Input characteristics. As I talk about input characteristics, we'll talk about the input terms. What are my input terms? That is my IB and VBE. So input characteristic, it's a graph between IB and VBE when VCE kept constant. Okay, it's a graph between IB and VBE when VCE is kept constant. So this is my VBE, this is my IB. We'll see the graph comes up like this. Okay, it's not starting from the origin, it rises after some time. I'll tell you why. VCE is equals to 4 volt and this is VCE is kept constant at 10 volts. That's my VBE, that's IB. Now what are the facts about it? Very, very important. What are the facts? Now what does the fact says? For the input characteristic, as long as your VBE is less than, your barrier potential. Now as this junction is forward biased, we have done the diodes also. In the diode, what was my observation? My observation was as soon as will not cross the barrier potential, there is no current. As you can see from here, as long as your VBE is 0, there is no IB, there is no current. But as soon as you start increasing your VBE and your VBE is able to cross your barrier potential of the forward junction, the current will start rising and current will increases rapidly as in the forward characteristic of the diode. This is almost similar to the characteristic of the forward biased junction diodes that you have studied, PN junction diode, no? Of the same. So as your VBE is very, very small, IB is 0. As VBE is greater than barrier potential, IB increases exponentially and then it becomes independent of VCE. As you can see, there is not much of the effect of VCE on the IB. So by plotting one of the characteristic, that is more than sufficient. By one characteristic, you will come to know about it. Okay, that is my input characteristics. Let's now talk about the output one. Output characteristic is a graph between, that is my output current. It's a graph between output current. What is my output current? That is IC. It's a graph between IC and VCE when IB is kept constant. Okay, when IB is kept constant, it's a graph between IC and VCE. So how we observe that the graph comes up of this form. This is my IC, this is my VCE. The graph is of this kind. Okay, this is IB is equals to 0, IB is equals to 0 microampere, IB is equals to 40 microampere, 80 microampere and 120 microampere. Okay, this is my saturation region. This is cut off and this one is active region. your transistor is most applicable in this active region. Okay, this cutoff, saturation and active region. Let's talk about this first. As you can see from here, see the graph first. Initially, when my VC is 0, my IC is 0. As I see from here, my IC increases to some point till your VC increases and reaches to the knee voltage. And then it becomes almost constant. Not exactly constant, but almost constant. Then increases there's a small increase over here. Similarly, if I increases IB, this knee voltage value increases and your IC increases to more value. As IB increases, IC also increases. So these are my two observations. The very first observation I am writing down is IC increases initially as VCE increases till knee voltage, and then small increase. And my second observation says as IB increases, IC increases. Let's now draw these two observations on my circuit. Let's see what it shows in the circuit. These two observations we will see in the circuit now. Parallelly, we'll have a circuit in front of us and we will see the characteristics. So that we'll come to know what we have done. Now, as you can see from here, initially when your VCE is very small, as you can see from here, this is very small. This junction is not at all. This junction is not forward biased. So your VCE is very small. Both the junctions are forward biased. As your VCE reaches to the knee value, your value of VCE will become greater than your VBE. Then your one junction will become reverse bias, the other will become forward bias. By the time your VCE is small, VCE is less than VBE, both the junctions are forward biased. As both the junctions are forward biased, the current increases till this value. As soon as your VCE become greater than your VBE, one junction will become forward, another will become reverse, and your current saturates. Okay? So in this saturation region, your both FB, both the junction are forward biased. In the active region, one forward and one reverse. Okay? Now as you see from here, if I increases IB, if my IB increases, that means my VBE increases. IB increases, VBE also increases. So as IB increases, VBE increases, and hence VCE will take more value to reach to reverse bias condition, and hence IC would be more. So now we have seen the output characteristics. Let's now talk about the transfer characteristics. Transfer characteristics is a graph between IB and IC. As you can see, IB is directly proportional to IC. IB increases, IC also increases. That's milliampere, and this one is microampere. That would be the end of this transistor. I hope you understand. Please see to this. If you have any queries, you can visit to us at Pious Learning, and the Facebook link is given to you. You can see and you can post your doubts, any queries you have. We will definitely try to resolve it. Thank you so much listening to me. Thank you.